I'm going to talk to you a little bit about some of our experiences on Summit with Flash Code, which is one of the car projects that's targeting Summit. And so the results I'm talking about today, they're either going to be done on Summit or on the early acceptance system, Summit Dev. And so basically, I'll tell you a little bit about kind of the scientific motivation for the problem we're trying to solve, and then go into a little bit more detail about what we've done. So, so really the motivating question that's driving the work that I'm going to describe is what is the origin of the elements? And so other than hydrogen and helium and a little bit of lithium, which come from the Big Bang, everything else comes from supernovae, pretty much. And so, so we're interested in modeling these. And so I don't know if you don't know what a supernova is. So these are some pictures you might have seen from NASA. They've put these out over the years. But what you're seeing are different elements in these pictures. And so we want to model these accurately and get a feel for how the elements in the universe are made. And that's becomes a computational challenge as the number of elements gets larger and larger. So we do this with the Flash code, and so Flash is a before we got a hold of it, it was just an MPI, OpenMP code, but it's been used at largest of scales. It's block structured AMR code. It basically works under this premise of you have some block that represents a region of space, and you're going to perform some physics operation on that block that's local. And then global operations will be handled separately. So it's been used in astrophysics, it's been used in laser physics and high energy density physics. So it's got a large community behind it. And for us in particular, it's the multi-physics capability that it has that makes it ideal as a code for us to target. To answer this question of what is the origin of elements. And so those multi-physics capabilities we're going to talk about today are the nuclear kinetics, where we're taking the approach of really trying to speed this up using GPU-enabled libraries, and also the equation of state, which we're taking a directive-based approach. Some other physics that's in there that we haven't started looking at yet are hydrodynamics and self-gravity calculations. So self-gravity is a communication-based operation, so we're not targeting that for GPUs yet. But the hydrodynamics is actually, there's a little bit of hiccup there because there was supposed to be a new solver, hydrodynamic solver that is coming soon, and we didn't want to waste too much effort on a solver that would be obsolete in a few months. So my main focus of all of this is the nuclear kinetics, and so you have a nuclear composition that's basically evolved at each time step, and this composition forms a nuclear network. And that network is evolved according to some coupled set of ODEs, which are very stiff, and so they require an implicit time integration. And so an implicit time integration means a matrix solve. And so the system that we're solving is relatively dense at the network sizes that we're interested in. And so the number of flops goes as n cubed. So traditionally, on CPUs, this is limited to something like 14 nuclear species. And that's enough to roughly get the amount of energy release that comes from burning correct. But you can't really say detailed things about what the composition is, what elements are being produced. And so the science goal, or it's really kind of the science push behind this, our car focus, is to replace a small network of 14 species with something more on the order of 200 species. And so just to give you an idea of what that looks like, so these alpha symbols are the small network, and we're expanding to the region that's encompassed by this dashed line. And so that represents something like more than a factor of 100 in terms of the actual computational load. And so I already told you about that. So I told you about the system of equations, but this is also being implemented, in addition to Flash, is going into a shared set of microphysics, a repository of shared microphysics that's being shared among multiple codes, not just Flash. So this is kind of the structure of what the nuclear burning looks like with the CPU. So we have some number of zones that are local to an AMR block, and so we loop over those, and then for each of those we have a sub-cycling in time that happens that's bound by some global time step. And so within that sub-cycling, for each time step, we build a linear system, we form an LU decomposition, and then we do the back substitution. And then we check and see if we're converged, and if we've reached the final time step, et cetera, et cetera. But that's all done inside of the OpenMP. And so this is what this kind of looks like now after the GPU port. So instead of just doing a loop over zones, these zones get grouped together into different batches. And so now the loop is over the number of different batches that we have. And that is parallelized with OpenMP. And then within that we have the time step loop. But now, because we've divided these zones into batches, we have these different batch operations that we perform during the integration. And so that's where we use directives. Here I have an example that uses OpenACC. We're also trying this with OpenMP. But we'll use directives to construct a linear system. And then we use these batched Kublas operations to do the linear algebra. But then we're still sending the results back to the CPU to do things that, there are some operations that we're not able to put on the GPU right just yet, and so we have to send the results back and control the actual time step loop with the CPU. But so many of the flops are in the linear solve that it's really, the data copy there is fairly negligible. So, so I said a little bit about AMR, and so traditionally, the way that the AMR in Flash works is that you have some criteria that in the fluid that you use, you look for gradients in that variable, and then you refine on that, and then you get a grid, and then you basically just distribute your MPI ranks across this grid uniformly. You don't really every block in this deconstruction has an equal weight, and you just fill it with a Morton space filling curve. But with burning, with these expensive nuclear burning, this turns out to be a little bit more of a challenge. So here is an example from a simulation that we ran where on the left, this is the number of sub-time steps that the burner is taking, and that there are hot spots, and these can really dominate the cost of the simulation. And so if you just take the naive approach where you don't weight the space filling curve, we run into a really big problem with load balancing. And so the solution to that was to weight the Morton space filling curve based on the maximum number of time steps taken by any single cell on a block. And that way we don't completely eliminate the load balancing problem, but it does help to ameliorate it. So these are some of the testing results. So this is single node, strong scaling. We had some problems early on when we first had access to the machine with the problem we were trying to run. We were having it crashing. It was a bug in our code. That's since been resolved. We haven't had a chance to go back and do scaling tests for larger numbers of nodes. But we're really interested in single node performance anyway, because that's where we're going to see the improvement in the linear solve. So we tested this single node strong scaling performance with the new burner, this test consists of evolving a three-dimensional block of zones per NPI rank that's initialized to some has some fuel mixture, and then we basically light a match and let it burn. And this is a pretty fair representation of the target problem for the car project. So in the top right plot here, I have the time to solution versus the size of the batch. How those cells get divided out into batches, and so from that we're able to pick out kind of an optimal batch size based on the number of zones, and this one turned out to be about 32 or 16. That's going to vary depending on the particular architecture, but for Summit, worked out. That's what it worked out to be. Okay, and here in the bottom line, this is the scaling plot. So the black line is the CPU, and up to some number of OpenMP threads per rank, where the ranks are distributed such that we have one MPI rank per GPU. And so if you were using all the cores, each rank would have 7 physical cores available to it. And so we see fairly perfect scaling with threading, and the difference here between the CPU and the GPU is about a factor of 2.5. And just to give an idea going forward, so this was for a network of 160 species, which still has some limitations to it. We want to move forward to something like 300, and there we did a test problem, and the speed up was about a factor of 3. So this work was primarily concerned with increasing the physical fidelity of the simulations by enabling something like an order of magnitude increase in the size of the reaction network. And so this is fairly important for the scientific community. So Flash, we can now use Flash to address some fundamental scientific questions that we really weren't able to do before. And so this kind of addresses this point that with these, as we go towards exascale architectures, it's not necessarily how much faster is your code, it's what science are you enabling. And I think that's an important thing to remember. And so with these new classes of simulations that we're running on Flash, we're going to be able to help inform other projects. So there's this effort project where they need measuring nuclear reactions and masses for very heavy isotopes, and we use these simulations are going to help inform those. So the other component of this is the equation of state, and so this equation of state basically provides a closure to the thermodynamic system. It gives pressure as a function of the other state variables, and the equation of state that we use for stars usually is called the Helmholtz equation of state, but it's based on a high-order interpolation of a table that's done for the Helmholtz free energy. And so there's an OpenACC version of this, was developed by some of our collaborators in the shared microphysics repository that we then wanted to implement in Flash. And so we had to kind of restructure some of the way that Flash operates with the equation of state in order to be able to take advantage of that, because we really wanted to be able to operate on all of the local cells at once so that we can give the GPU a significant amount of work to do. And so the question we kind of started with was how many AMR blocks do we really need to evaluate the EOS for this to pay off. And so we used a mini app driver to test this, and it mimics kind of the structure that we see in Flash, where we have through a loop over several time steps, and then within that loop we have a loop over several zones. For each of those zones they call an equation of state. And so the basic workflow does something like allocate the main data arrays on the host and the device. And so these are arrays of Fortran derived types, and they're global data that persist for the duration of the program. And then we use a reduced data set for the copy in, basically only the input state, and then we copy out the full state, including things like internal energy and pressure and entropy. So we begin by reading in a table and make a copy on the GPU. And this is where the interpolation is done. And then for each time step, we update the device with the new data, we launch the kernel, and update the host. So this is what this actually looks like in code. So we compared OpenACC and OpenMP 4.5. So we have our loop over zones, and they each call the equation of state. And this equation of state, this is coming from the external microphysics repository. And so that's an ACC routine. In this case, OpenMP. So all these tests were actually carried out on Summit Dev. These were done a while ago. Let's see. That's just talking about the architecture. So I do want to say before I actually show you the results, though, that when these benchmarks were actually done, that PGI's OpenACC implementation already had a mature API, and for OpenMP 4.5, we were using XL, which was at the time was in a beta version and did not have full support for the standard. And it also did not allow to have the pin memory or asynchronous data transfer going between the host and device, and so that put it in some of the performance numbers. So here on the left, we have OpenACC for different numbers of CPU threads that are each launching kernels, and then on the right, OpenMP 4.5 under the same paradigm. And so the x-axis here is basically the number of blocks, where basically we're increasing the number of zones that we're calculating at once as we go along the x-axis. And so you would think that at high enough zone counts that all the overhead would go away, and we would think that OpenACC and the OpenMP implementations would converge to a similar number. But when we ran these tests, they did not, and that's the OpenMP was a factor of 5 or so slower than OpenACC. But this has since been addressed, but I don't have new numbers for that. So at low block counts, the kernel overhead actually dominates the cost, and it's large relative to the compute time, and we kind of took the strategy of having multiple CPU threads, stagger the host to device transfers to try to get the cost down. But this just added even more of an overhead cost, which can be seen here. Basically, each of these is a hosted device memory copy, but every time we did that, we incurred a little bit of synchronization. At the higher block counts, the kernel overhead goes away, but now we're back to being dominated by the data copy back to the host. So these are the OpenMP results that we had, and so I don't want to spend too much time on these because the API was so so much in its early stages at that time. But we were able to kind of use these to kind of pinpoint some areas that needed development, and those have since been addressed. So what we ended up with was we were able to find kind of this optimal configuration of how many blocks we really need to be able to use this OpenACC implementation of the equation of state efficiently. And it works out to be something about if we have more than 100 blocks in 2D, or it's just 6 in 3D, then we want to use this GPU version of the equation of state. So OpenMP kind of provides us with looking forward. We want to kind of use more OpenMP because of portability reasons. But despite the lower performance that we saw in this test, we still plan to move forward as those issues get fixed. But in general, we find that the best balance between the CPU threads and the block numbers occurs at 2 to 4 threads and roughly 1,000 blocks. And we saw a speed up of about a factor of 10 relative to the CPU. So kind of pulling it all together, we had a very positive experience so far with Summit. We did have some issues with using we had a flash I/O benchmark that we ran that we saw some peculiar behavior in parallel HDF5 that's currently trying to be fixed. We don't. The problem is in MPI/IO, and so we don't know why this slipped under our noses for a little while. But we're glad we caught it before January. And so with all of the upgrades to the nuclear burning and the equation of state in Flash, we were getting a speed up of anywhere between 2 and 3x, depending on the particular problem relative to the CPU alone. But we still have a lot we want to do, including looking at the new Hydrodynamics solver, implementing a gravity solver that uses GPU Direct, and then eventually we're going to move towards other types of problems that use radiation transport. And when we do that, radiation transport will become the dominant computational. That's going to be where all of the flops are in the problem, more so even than a large reaction network. And so we want to make sure that we have an efficient GPU implementation of that when that time comes.
Thanks a lot. Thanks so much.